This is a question from GATE 2006. A medium is divided into region 1 and 2 about x equal to 0 plane as shown in figure below. An electromagnetic wave with electric field E1 equal to 4ax plus 3ay plus 5az is incident normally on the interface from region 1. The electric field E2 in region 2 at the interface is option A E2 equal to E1, option B 4ax plus 0.75 ay minus 1.25 az, option C 3ax plus 3ay plus 5 az, option D minus 3ax plus 3ay minus 5 az. So in this question it is given that there are two regions, region 1 and region 2. There is a boundary between region 1 and 2 at x equal to 0. In region 1, mu1 equal to mu naught, epsilon r1 equal to 3 and conductivity is 0. And electric field in region 1 is E1 equal to 4ax plus 3ay plus 5az, that is for x less than 0. In region 2, we have to find electric field intensity. In region 2, we have to find electric field at the boundary. So in region 2, mu2 equal to mu naught, epsilon r2 equal to 4 and conductivity is 0. Now, as we can see that it is boundary is at x equal to 0. It means that this will be the x-axis because here x is variable. As we can see that this axis will be x-axis because here x equal to 0 and here x less than equal to 0 and here x greater than 0. So we can consider it as x-axis itself. Because in this axis, in x-axis, x will be the variable and here x is changing continuously. Many students get confused with x equal to 0 plane. What should be the x equal to 0 plane? So for that, as we can see here x is variable and we always use right hand coordinate system. So according to the right hand coordinate system, if we take curl of x and y, we will get z. If we take curl of y and z, we will get x. And if we will take curl of z and x, then we will get y. Z cross x will get y. So here this is x equal to 0 is the interface. Here we are seeing only a single line. It means that this is x-axis, this is x-axis. If we curl my finger from x to y, we will get the direction of z. So this is x. So this is x. If I curl my finger from x to y, then the thumb will be the direction of z. So this is x and we have to take this line as y because this is positive x. So this is x. If I curl my finger from x to y, thumb will be the direction of z. That means z is the outside the board. Z will be the direction of outside the board. In this direction, z will be the outside the board. So if z is this, then we take x cross y, we will get direction of z. So here we can see that z is nothing but outside the board, and outside the board we can denote by dot. So here the plane is like this. This is the plane which is boundary between or which is interface of region 1 and region 2. So from there, from this side we can see this line only, and this line is nothing but y-axis. This line is nothing but y-axis, and this line which is outside the board is nothing but a z-axis. So this is y-axis and this is z-axis and this is x-axis. So x to y, we are moving from x to y, we are getting z direction which is outside the board. So x equal to 0 means which plane? So we can see this as a plane. So this is the plane will be x equal to 0. That means this is y line and this is z axis. So the x equal to 0 means yz plane. X equal to 0 means yz plane. So x equal to 0 means yz plane, and this is z axis. Z is outside the board, and this is Y. So now it is clear that if we say x equal to 0 means the boundary or the surface is YZ plane, which is the interface of region 1 and 2. Now from boundary condition, we know that tangential component of electric field in region 1, is same as tangential component of electric field in region 2. From boundary condition, at x equal to 0 or x equal to 0 plane or at the interface, tangential component of region 1 is same as tangential component of electric field in region 2. Now what should be the tangential component? So as we can see, this is x equal to 0 plane. X equal to 0 means YZ plane. So the parallel component, if this is Y, if this is outside the board is Y, and this is Y axis, and outside the board is Y, then tangential component of electric field at the boundary will be Y and Z, because Y will be in the direction of Y axis, Y component of electric field will be in the direction of Y axis, means it is parallel, or we can say it is tangential to Y axis. And similarly Z component for interface Y and Z will be the tangential component. So 3AY plus 5AZ, this will be the tangential component of electric field in region 1 at the boundary, and tangential component of electric field in region 2 will also be same from this boundary condition. So we have tangential component of electric field as 3AY plus 5AZ. Put it equation number 1. Now from boundary condition, at x equal to 0 we know that normal component of flux density in region 1 is same as normal component of electric flux density in region 2. So dN1 equal to dN2, and flux density is given by epsilon 1 En1 equal to epsilon 2 En2. Flux density equal to permittivity and normal component of electric field. Flux density is epsilon E. So here flux density, normal component of flux density is given, so En1. Now epsilon 1 can be written as epsilon R1 epsilon naught En1, and this can be written as epsilon R2 epsilon naught En2. Normal component of electric field will be now epsilon R1 divided by epsilon R2 into En1. So epsilon R1 is 3, epsilon R2 is 4, and normal component of electric field. So normal component of electric field will at the interface will be x equal to 0 planes, means YZ plane, and the normal component of YZ plane will be x itself. So YZ, normal component of YZ will be x. So normal component of electric field in region 1 will be x component, that is 4AX. So this is 3AX. Now this put it equation number 2. Now we have tangential component of electric field in region 2. We have normal component of electric field in region 2. So we can write electric field, total electric field in region 2, which is sum of tangential component plus normal component. So tangential component is 3AX. So tangential component is 3AY plus 5AZ, and normal component is 3AX. So we can write it as 3AX plus 3AY plus 5AZ. So electric field in region 2 is 3AX plus 3AY plus 5AZ. Hence the correct option is option C. This is the question from GATE 2009. two infinitely long wires carrying current are as shown in figure below. One wire is in the YZ plane and parallel to the Y axis. The other wire is in the XY plane and parallel to the X axis. Which component of the resulting magnetic field are non-zero at the origin? Option A, XY Z component, option B, XY component, option C, YZ components, and option D, XZ components. So there are two current carrying elements or conductor. So the first conductor is placed parallel to the Y axis, which is carrying current 1 ampere, and other conductor is also carrying current 1 ampere, which is parallel to the X axis. We have to find magnetic field at origin. What are the frequency components which is not equal to 0 at origin? So to find the direction of magnetic field or the component of magnetic field, we can apply the right hand rule. Right hand thumb rule. According to the right hand thumb rule, if thumb is the direction of current, then the direction of magnetic field is calculated from the direction of finger curls. Means that if the thumb is direction of current, then in the direction where the finger curl will be the direction of magnetic field. So here we can see that this is X axis, this is Y axis, and this is Z axis. That means if we take curl from Y to Z, or if we curl finger from Y to Z, then thumb will be the direction of X. First of all, we have to understand what is the direction of X. So Y to Z, if we curl finger from Y to Z, then thumb is pointing in the direction outside the board. That means this X axis is nothing but outside the board. So we have X axis like this. So this is X axis, this is Y axis, and this is Z axis, because when we curl from X to Y, then thumb will be the direction of Z. So if this is the direction of X, then we curl from X to Y, then we curl from X to Y, then this will be the direction of Z. Similarly, Y to Z, when we curl from Y to Z, then thumb will be the direction of X. Or when we curl from Z to X, thumb will be the direction of Y. So X is outside the board. Now we have to find direction of magnetic field or component of magnetic field at origin. So if we apply the right hand thumb rule, so thumb is the direction of current, and this is nothing but in the direction of X axis. So the current is flowing in the positive X axis, and we know that this X axis is nothing but outside the board. So this is the direction of current. So thumb is the direction of current, which should be outside the board, because X axis is outside the board. So direction of thumb should also be outside the board, because current is flowing in the positive X direction. So we have direction of current like this. Now if we curl finger like this, then at origin the direction of finger is, what will be the direction of finger? So if this is the direction of current, and if we curl finger like this, then here if we curl finger like this, then at origin my finger is going in the negative Z direction. Where it is going? So this is the direction of current. I am curling my fingers. I am curling my finger at origin. So at origin my finger is downward. Downward means it is in the negative Z direction. In this direction. This is negative Z direction. So from here, when I curl my finger according to the direction of current is positive X axis. So if I curl my finger at origin, this is pointing in the direction to negative Z direction. It is pointing in the negative Z direction, or it is pointing downward. So this is in Z direction. So minus Z component will exist. minus Z component will not be 0 at origin due to current carrying conductor which is carrying current 1 ampere. Now we can apply the right hand thumb rule for this conductor. So according to for this conductor the direction of current is in the positive y direction. So we will put our thumb in the direction of current. So if I put my finger like this, then thumb is the direction of current. So this is the direction of current. Now if I curl my finger, then at origin it is, if I curl my finger like this, then at origin it is going inside the board. You can see that when the current is in this direction, so thumb should point in the direction of current, and this is nothing but origin. Suppose this is origin, then if I curl my finger like this, then finger is moving inside the board. So outside the board is positive x-axis, so inside the board will be negative x. So minus x component will also not be 0. So x component and z component will not be equal to 0. This is minus x component because of this current carrying conductor, and this is minus z component because of this current carrying conductor. So x and z component will not be equal to 0. And this is by using the right hand rule. If someone finds difficulty in applying right hand rule, so we can also calculate direction of magnetic field by using mathematical expression. So direction of magnetic field can be calculated from this expression, which is unit vector, cross product of unit vectors. So direction of magnetic field AH cap equal to AL cross arrow, where AL is the unit vector in the direction of flow of current, and arrow is the perpendicular unit vector along perpendicular distance from conductor to point of interest. So here for conductor parallel to x-axis, what will be the direction of magnetic field? So for conductor parallel to x-axis means this one. So for this particular conductor, what will be the direction of magnetic field? So AL is the unit vector in the direction of flow of current. So the current is flowing in the positive x direction. So AL will be AX cap, cross product with perpendicular distance from conductor to point of interest. Perpendicular distance from conductor, this is also parallel to x-axis, means outside the board, and perpendicular distance from this conductor to point of interest is origin. So if I draw perpendicular distance from this point to this point, this is nothing but in the direction of minus y. So this is nothing but direction of minus y. So arrow is in the direction of minus y. So this is nothing but minus AZ, which we have found from right hand thumb rule also. Minus Z component will not be equal to 0. So because for conductor parallel to x-axis, AH equal to AX cross minus AY, using this formula, so the direction of magnetic field is in the minus Z direction. Similarly, for conductor parallel to y-axis, so what will be the direction of magnetic field now? Similarly, we can apply here again AL is in the direction of current flow. So the current is flowing in the positive y direction. So current is flowing in the positive y direction. So AL is AY, and perpendicular distance from conductor to point of interest. So if I draw perpendicular line, from this point to this point, this is our conductor. If I draw perpendicular line to this point, this is nothing but in the direction of minus Z. So this is minus AZ. So AY cross AZ is plus AX, and because of this minus sign, this is minus AX cap, which we have found from right hand thumb rule. So it means that the X component and Z component will not be equal to 0 at origin. Hence the correct option is option D. This question is asked in GATE 2011. A current sheet J equal to 10 AY cap ampere per meter lies on the dielectric interface X equal to 0 between two dielectric media with epsilon R1 equal to 5, mu R1 equal to 1 in region 1, which is X less than 0, and epsilon R2 equal to 2, mu R2 equal to 2 in the region which is X greater than 0. If the magnetic field in region 1 X equal to 0 minus or X less than 0 is H1 equal to 3 AX cap plus 30 AY cap ampere per meter, the magnetic field in region 2 at X equal to 0 plus is option A, H2 equal to 1.5 AX plus 30 AY minus 10 AZ, option B, S2 equal to 3 AX plus 30 AY minus 10 AZ, option C, S2 equal to 1.5 AX plus 40 AY, and option D, 3 AX plus 30 AY plus 10 AZ. So in this question, there are two regions, region 1 and region 2. Again, region 1 is for X less than 0, and X equal to 0 is the interface between region 1 and region 2, and region 2 is X greater than 0. It is given that this is X axis and this is Y axis. It means that and the magnetic field is H1, which is 3 AX plus 30 AY, and region 2 is described by or characterized by epsilon R2 equal to 2 and mu R2 equal to 2, and this interface is carrying current 10 AY. So here this is the current is flowing in the Y direction because this is 10 AY, so the current is flowing in the Y direction, and from figure also this is X axis and this is Y axis, so current is flowing in this direction, means Y direction. And if this is X, because in this line X is variable because X is changing from negative to positive, so this is X axis because here X is variable, so this is completely X axis. Now if I curl from X to Y, from right hand coordinate system, so this is X to Y, so Z will be in the direction inside the board. So this is in the direction of Z. Z will be the inside the board because inside the board thumb is pointing inside the board when I curl from X to Y. When I curl from X to Y, thumb is in the direction inside the board. So positive Z will be in the direction inside the board. Now, so this is YZ. Now the interface between region 1 and region 2. So the interface between region 1 and region 2 will be like this. So we can see this line only, which is Y axis, and this will be inside the board. So this is Z axis, and the normal of this sheet, the current is flowing in this sheet uniformly. This 10 AY is the current flowing in the sheet, and the sheet is nothing but a surface which is interface of this two region. So this is the interface and this is the direction inside the board, that means this is the Z and this is Y, and X will be the normal component. So from this figure also we can see that this is Y axis, and X is normal to this surface. So X is normal to this surface, and this is inside the board. So this is inside the board is nothing but a Z. So this sheet is nothing but a YZ plane. X equal to 0 is the interface, that means YZ plane, and the YZ plane is the interface of X and Y which is carrying current uniformly 10 AY, current density 10 AY. Now we have to find H2 in region 2, which will be nothing but sum of tangential component plus normal component. Magnetic field in region 2 will be sum of tangential component and normal component. Now from boundary condition, at the interface, that is at x equal to 0, we know that normal component of flux density, magnetic flux density in region 1 is same as normal component of magnetic field, then magnetic flux density in region 2 is same. Normal component of magnetic flux density in region 1 is same as normal component of magnetic flux density in region 2. Now we have magnetic field intensity in region 1. So magnetic flux density can be written as mu1 Hn1, mu2 Hn2. So we have to find Hn2, normal component in region 2. Mu1 can be written as mu naught mu r1, mu2 can be written as mu naught mu r2 and Hn1. So mu r1 is 1, mu r2 is 2 and Hn1, normal component of magnetic field. So here normal component, as we have seen that x equal to 0 plane, that means yz plane. So if this is yz plane, then x will be the normal component. If this is yz plane, then x will be the normal component. So normal component will be x component and this is nothing but 3ax. So this is 1.5 ax cap. So normal component we have calculated. Now we have to calculate tangential component. So again from boundary condition, tangential component, if j is not equal to 0, then the tangential component is given by h1 minus h2 cross an equal to j. And if suppose j is 0, if the interface is not carrying any current, then j will be 0, and for that we directly write st1 equal to ht2 for j equal to 0. For j equal to 0. But here we have interface which is carrying current in the direction of y. So current density j equal to 10 AY. So h1 minus h2 cross an equal to j. An is the unit vector normal to the interface. Here interface is x equal to 0. X equal to 0 means yz plane, and the normal component of yz plane is nothing but x itself. Normal component of yz plane is x. So an will be ax here. And here we have written h1 and h2, not ht1 and ht2, because this gives only tangential component. Normal component will automatically goes to 0, as we will see it. h1, so h1 is 3ax plus 30ay. This is h1 minus h2. h2 will have, h2 may have x component, y component and z component. Okay, because I am taking general expression, here h1 and h2 we are not considering only tangential or normal component, so we will write all the components, because h2 can have x, y and z component, and we will see this, that normal component will automatically goes to 0 and we will left with only tangential component. So here h1 minus h2 we can write, but when j is 0, then we directly write tangential component of magnetic field intensity in region 1 is same as tangential component of magnetic field in region 2. Cross ax and 10 ay. So if it cross product this x cross x, this will go to 0, and y cross z is minus az. So this is 30 minus 30 az. When we take cross product of y and x, we will get minus az. Now this is minus x cross x will be 0, y cross x is minus, and because of this minus this will be plus hy az, and z cross x is plus ay. So this is minus here, so this is hz ay, and this is equal to 10 ay. Now we have hy az minus hz ay equal to 10 ay plus 30 az. So on comparing these two, we will get az component have coefficient hy and z component has coefficient 30. So we will get hy equal to 30, and y component having coefficient 10, here y component having coefficient minus hz. So hz is minus 10. So in this way we can get the coefficient, or we can get the tangential component, because y and z are tangential component. For x equal to 0 interface, y and z are tangential component, and as we can see that the normal component will automatically is 0. The normal component automatically goes to 0, because x cross x will be 0. So normal component, we will left with only tangential component, that is y and z. So we have calculated the normal component, and now we have y and z component, that is tangential component. So magnetic field in region 2 is tangential component plus normal component. So tangential components are 30, this is y component, so 30 ay, plus tangential component, again this is minus 10 z component, so the unit vector will be in the direction of z, and normal component is 1.5 ax, and hence h2 will be 1.5 ax plus 30 ay minus 10 az. So magnetic field in region 2 is 1.5 ax plus 30 ay minus 10 az. Hence the correct option is option A. This question is asked in GATE 2016. Concentric spherical shells of radius 2 meter, 4 meter and 8 meter carrying uniform surface charge density of 20 nanocoulomb per meter square minus 4 nanocoulomb per meter square and rho s respectively. The value of rho s in nanocoulomb per meter square required to ensure that the electric flux density D equal to 0 at radius 10 meter is. So in this question it is given that there are 3 concentric spherical shells having surface charge density rho s1 with radius 2 meter, surface charge density rho s2 having radius 4 meter, and surface charge density rho s3 having radius 8 meter, and the surface charge density at rho s1 is 20 nanocoulomb per meter square, rho s2 is minus 4 nanocoulomb per meter square, and we have to find rho s3 surface charge density of on third spherical shell. And it is also given that at distance 10 meter from the center, flux density is 0. Flux density is 0. So now from the Gauss law, we know that total electric flux passing through any closed surface. So total electric flux passing through any closed surface is given by d dot ds. Flux passing through closed surface is given by integration over the closed surface d dot ds. the flux passing through the closed surface is equal to charge enclosed by that closed surface. So total electric flux passing through any closed surface is equal to charge enclosed by that closed surface. So to find the total electric flux, we have to draw the Gaussian surface. So for that, we have to find flux density at 10 meter. So we will draw the Gaussian surface at 10 meter, because it is given that at 10 meter flux density is 0. So if the flux density is 0, then charge enclosed at that point will also be equal to 0. The flux density is 0, then the flux will also be 0, or we can say that the charge enclosed by that Gaussian surface is also 0. Here the flux density is 0, so the flux passing through the closed surface, that is denoted by xi. So this xi will be 0 because d is 0 at 10 meter, or charge enclosed will also be equal to 0. So this is nothing but a Gaussian surface. To apply Gauss law, we have to draw the Gaussian surface, and Gaussian surface should be a closed surface. So at 10 meter d is 0, and for d is 0, xi is 0, and xi is 0, or we can say charge enclosed is 0. So this Gaussian surface enclosing the charge, that is the charge carried by rho s1, rho s2 and rho s3. The charge enclosed by this closed surface, this Gaussian surface, is charge stored or in rho s1, rho s2 and rho s3, or the 3 concentric spherical shell. So charge enclosed should be 0. So charge enclosed is on first concentric sphere is Q1, second sphere is Q2, and third sphere is suppose Q3. Then the sum of this all the charges should be 0. The charge enclosed by Gaussian surface should be 0. We know that the charge is dq equal to rho s into ds, or if we integrate it over the surface, then we will get the total charge, that is nothing but rho s into area. So total charge stored in first sphere, if we know the surface charge density, then this will be nothing but a rho s into its area. So Q1 will be rho s1 into area of sphere. For first sphere this is 4 pi r1 square, plus for second sphere the charge stored is rho s2 into 4 pi its radius, that is r2, and this is rho s3 for third sphere 4 pi r3 square, and this should be equal to 0. So 4 pi rho s1 value of rho s1 is 20, and 4 pi r1 square, the radius is for first sphere, the radius is 2, so this is 2 square, plus this is minus 4, and 4 pi second radius is 4, so this is 4 whole square, plus rho s3 we have to find, and 4 pi r3 is 8, so this is 8 whole square, and this should be equal to 0. So this is 4 into 4, 16 into 2, 320 pi, minus 16 into 4, 16 into 4, 64 into 4, yeah, okay, minus 256 pi, plus rho s3, this is 64 into 4 again, 256 pi, and this is equal to 0. So if we solve this for rho s3, we will get 320 pi minus 256 pi divided by 256 pi. So after solving this, we will get minus 0.25 nanocoulomb per meter square, because this 20 and 4 are in nanocoulomb per meter square. So the result of rho S3 will also be in nanocoulomb per meter square. So the charge density in third sphere is nothing but minus 0.25 nanocoulomb per meter square. This is the question from GATE 2016. The parallel plate capacitor shown in figure has movable plates. The capacitor is charged so that the energy stored in it is E when the plate separation is D. The capacitor is then isolated electrically and the plates are moved such that plate separation becomes 2D. At this new plate separation, what is the energy stored in the capacitor neglecting fringing effects? Option A 2E, option B root 2 times E, option C E, and option D 1 by 2 E. So in this question we have parallel plate capacitor. When the separation between the two plates of capacitor is D, energy is given by E, and we have to find energy when the plate separation is 2D and this capacitor is isolated electrically, or electrically isolated we can say. So electrically isolated means what? If we connect the capacitor by battery for some time and when we remove the battery, then it is called electrically isolated. When we connect the battery in the capacitor for some time and when after some time we remove the battery, then it is called electrically isolated. And when the capacitor is electrically isolated, the charge in the capacitor is same. When we connect the battery, the charge is stored in the capacitor, plate capacitor, and when we remove the battery, the charge is stored in the plate capacitor. This is same. So for electrically isolated, capacitor, charge stored in the capacitor is same. Charge stored in the plate or capacitor is same. So we have to keep this in mind. When we connect the battery for infinite times, like when the battery is not removed, then in that case voltage is same. Voltage across the capacitor is always equal to same. Always remember that when we remove the battery, the charge stored in the capacitor is same, and when we connect the battery, then voltage across the capacitor remains same. So here it is electrically isolated, that means charge stored should be same. Now in the first case, this is parallel plate capacitor. So for parallel plate capacitor, C equal to epsilon naught A by D. Yeah, simply epsilon A by D. So here we can see that the capacitor is inversely proportional to the distance between the plate. For parallel plate capacitor, C is equal to epsilon A by D, and C is inversely proportional to distance between the plate. Now energy stored in the capacitor. So energy stored in the capacitor in case of parallel plate capacitor, energy stored in parallel plate capacitor is given by, let us say, E1, and this is, or simply E 1 by 2 CV square, and we also know that Q equal to CV. So V equal to Q by C. So if we write this 1 by 2 C Q square C square, or 1 by 2 Q square by C. So energy stored in capacitor in terms of charge is given by 1 by 2 Q square by C. So in first case, in case 1, when separation is D, when separation is D, the energy stored is, let us say, E1, and this is 1 by 2 Q1 square upon C1. The capacitor is considered as C1 and charge stored in capacitor is Q1. Now in case 2, when separation is 2D, then from this expression we know that the capacitor is inversely proportional to distance. So if in this case C2 will be inversely proportional to 2D, or we can write it as C2 is C1 upon 2, because C1 is epsilon A by D, C1 is epsilon A by D. Now C2 is epsilon A upon 2D. So this epsilon A by D can be written as C1, and this will be C2 equal to C1 by 2. So capacitor, when we increase the distance between the plate, the capacitance is reduced. So energy is stored in this case when the separation is 2D is denoted by E2. This is 1 by 2 Q2 square upon C2. So 1 by 2 Q2 is same, Q2 equal to Q1, because charge should be same. So Q2 equal to Q1 we can write, charge stored is same, and C2 is C1 by 2. So this is C1 upon 2. We can also write it as twice of 1 by 2 Q1 square upon C1, and 1 upon 2 Q1 square upon C1, 1 upon 2 Q1 square upon C1 is nothing but E1. So this is 2 times of E1. So energy stored when the separation is 2D is nothing but 2 times of E1. Hence the correct option is option A.